we are very fortunate to have Russ Tedrake here from MIT. And Russ, thank you for visiting us in person. And Russ, I think all of you know, you can see from the crowd that people know who Russ is. So I don't have to enlist all of his awards that he has gotten from every organization out there. And he's currently also Vice President of Robotics Research at Toyota, along with his position at MIT. And I got to know more about Russ by looking through his courses on the website. So you may know of Russ's work, but if you really, one thing that really stands out of like the quality of courses Russ has delivered and the amount of lecture that is there online. And you can like, once he gives a course, you can make a book out of it by just printing it, I guess, like the way it is organized on the website. And he has gotten a teaching award as well in 2012 and a list of other awards. And I guess we see a lot of cool robotics results from Russ's talk today. But I'm saying that the thing that he's probably not going to mention today, like his work on locomotion and maybe over 10 years ago, was also as impressive as the results today in locomotion and these results we'll see today. So with that, let's introduce Russ to the talk.
Thank you guys for coming. It's awesome to be here in person. I'm really excited for that. So if anybody's not in person and they're watching on Zoom, I just put that link in the chat. One of the things that I learned about teaching over Zoom was that slides.com is pretty cool because people can watch my videos at full frame rate instead of watching through Zoom. So this, if you open that link in your browser, it'll advance and all the videos will download directly to your client and you don't have to have the lag and our beautiful robot videos still look beautiful. Okay, so yeah, I'm an old guy now and had to think about what to talk about. And now I really want to tell you about just one idea that I'm super excited about today, which is this advance that we've been making in motion planning. I would have put large language models in the title if I could, but I stuck with convex optimization, and I hope you'll stick with me here. So the story is really a story of two papers. One of them is the shortest path on graph of convex sets, which I hope you'll understand by the end, which is an optimization theory paper, if you will. So there's an optimization back end of this that has almost nothing to do with robotics. It's a general machinery. And then, but the main storyline today will be that how do you apply that set of tools to motion planning and the impact it could have in the way we plan complicated motions. So I know some of you are extreme experts in motion planning, but let me say a few very basic things to just set the stage. Okay, so in my view, I'm going to use like a very simple example to just talk through a couple of these ideas. So in this simple example, there's a point robot that has to go from the start to the goal and a red obstacle that it wants to avoid. Okay, so the shortest path problem from the start to the goal might give you a straight line trajectory to that vertex and back. Okay, and even though that's extremely simple, it's enough for me to sort of remind people that there's, in my mind, two important problems in motion planning for robots, two aspects of that problem. Part of it is a combinatorial problem. And sometimes we don't talk about that very explicitly, but really there is some discrete decision, some combinatorial decision about, am I going to go left around the obstacle or right around the obstacle? Okay, and that gets much richer in more complicated settings, but even in the simple one obstacle case, you have to make a decision. Am I going left or right? And then once you've decided to go left or right, you have some other optimization maybe to do to try to decide over some parametric curves. We typically talk about, what's the best decision? What is it going to be shortest path on the right? Is it going to minimize energy? Is it going to minimize torque? All kinds of things. And we're good at both of those problems somewhat independently, but we're not so good at doing them jointly. And I actually talked to a few of you today that have been talking about interleaving, planning and trajectory optimization. And that's my story is in that vein. Okay, so the combinatorial aspects maybe are easier to see if I take away the.
Yeah, good. Then
I'm hearing it.
Getting anything? Anybody speak? Yeah.
We're hearing you.
Ryan?
I'm supposed to be muted.
Oh, yours.
The audio is coming through here. You guys hearing us now?
I just got an email saying there's a different link for this.
It's the same link. It's the same link.
All right.
How do we tell them?
Chris, you can hear me, yeah?
Is Brian somewhere
I
here?
heard Chris's voice.
I think you should unmute.
I got an email 2 hours ago. You got one just now?
I can hear, yeah, right.
Oh, I got it. Yeah, I see it. See, all
There.
Okay.
right, for all you
Okay, is
people in chats,
Can they?
you don't have to. Well, someone beat you to it.
Can you guys hear us?
Yes,
Okay, yeah,
Yes.
it's just don't change.
Okay, and we can hear you too. So if you want to ask questions,
There are like
We're good for that.
70 people in there.
that's good. Okay, so the combinatorial side of the motion planning problem is exacerbated in, more complicated geometric environments. Of course, if you're trying to sneak a robot arm through a very complicated environment, maybe you'll see it like that. It can also be.
now you're echoing like crazy.
Yeah, I'm going to keep talking and hope somebody else could maybe come in and do their thing.
I think it was Stephen. I think so.
Okay. All right, so everybody sort of knows, I think we're solving some of these problems very well. And let's just remember that the way that we're solving it very well is typically with sample-based motion planning. When we have a strong combinatorial aspect of the motion planning problem, it's typically done effectively with sample-based planning. And we have PRMs, we have RRTs. I think the PRM, and I chose Howie's graphic here, the PRMs show it nicely because we explicitly, after we sample and make our roadmap, we solve a graph search problem, right? So we solve a search problem using our tools from combinatorial optimization or from graph search in order to find the shortest path. Graph search is a tool for combinatorial reasoning, and it's one of many tools. There's a huge library of combinatorial optimization and relaxations, okay? And it's being used very effectively in some of these problems. How you're kidding. I'm going to tell them about that. I got an email from the admin saying that's going to pop up at some point. I didn't. Okay, not the flow I normally would try for, but the other half of optimization maybe is trajectory optimization. Okay, so motions like this come out beautifully from a trajectory optimization solver, right? So I can just ask for my quadruped to move at certain speeds, maybe say something about the gait, and we optimize beautiful smooth motions. Now, if you've done a lot of work with sample-based planning, it'd be hard to imagine getting a sample-based planner to generate efficiently very beautiful motions like this. Okay, but at the same time, our trajectory optimization is going to fall down if you ask it to find a path through the maze. Okay, so my goals for today are mostly to do motion planning, right? I'm going to tell you about a specific new set of tools for doing global optimization. We want to solve the hard problems like sample-based planning can do, but also handling continuous trajectory optimization type constraints, dynamic constraints, curvature constraints, velocity constraints. Okay. But moreover, I've been thinking about why are we solving the same problem with different tools that should be more connected than they really are, right? We've got this trajectory optimization world and we've got the sample-based planning world, and we've got hugely scalable tools from AI style logical planning, right? Solving just enormous problems. And we have incredibly powerful tools from combinatorial optimization, and they don't always go together. They should be talking about the same truth, right? So can we do anything to bring these a little bit closer together? So the type of solutions that we're going to be able to get with this new method, I can showcase in a few examples. So this is testing my internet connection. There we go. All right, this is a quad rotor finding a minimum snap trajectory through an obstacle course. That's, there's a start, there's a goal, there's obstacles, there's complex obstacles. This would be hard for trajectory optimization, but it's solved to global optimality up to some, I'll give you some of the caveats in the class of parametric curves we solve for, to global optimality with convex optimization. So that, I think, that's the part that should be surprising. I think that we have a very reliable solver that will solve, always, or tell me no if it doesn't work. Maybe even more surprising to me was that we can do this kind of thing with, complicated bimanual manipulation. If we want to have to play Twister with some mugs to get the robot to move two arms around a shelf, This is a motion planning problem, a hard one with complicated configuration space obstacles, avoiding self-collision and getting into the shelf. And it's being solved to global optimality up to a class of parametric curves with convex optimization. Okay. And there's a few more examples. Here's some hardware. I was talking to Jeff before, but even the timing of the mugs and of when it's getting picked up, when it's getting set down, that's all coming out of the optimization. We're solving a big optimization that goes from the very beginning of that to the end, finding, to my eyes, beautiful, smooth trajectories by manual, running on hardware with convex optimization. Okay, a couple of just one other example, maybe. The fact that this other arm started moving well before in order to intercept just right, minimizing against all the, velocity limit constraints and the like, is something that I didn't have before. Okay, so let me just, the idea is very simple. The machinery is more involved, and I want to spend most of the time talking about the machinery. But the idea of how we're doing that is actually very simple, and it's not magical at all. If you like the PRM, the probabilistic roadmap version of sample-based planning, then you'll be right with me. So what we're advocating here is a PRM-like approach where we'll take samples. Well, the red regions are obstacles. We'll take a sample. If it's outside an obstacle, then we're going to do a little bit more work, and we're going to try to grow a big region around, instead of just connecting to nearby samples. I'm going to grow a big region and try to find a big convex region inside configuration space. Okay. And what that's going to do is, instead of having a topology, I'll grow a series of them. I'll put a connection between them in a graph if they overlap. Okay. And what that's going to do is, instead of having a search at the end, which is restricting me to just some line segments through space, it's going to leave room to do continuous optimization in a guaranteed collision-free manner at the end. Okay. So the picture evolves into something that looks more like this. Still take your samples. You'll still have probabilistic coverage of the configuration free space. You can sample until you've covered almost everything probabilistically, or you can take a coarse approximation. And then at solve time, when we would normally just do the graph search, we're going to do a combined continuous and discrete search to find the globally optimal curves that live inside the graph and find the way from the start to the goal. And that extra flexibility is going to allow me to take a lot of the strength of the sample-based planning, but bring in all the continuous dynamic constraints and everything from trajectory optimization and bring them together. So the claim is guaranteed collision-free along piecewise polynomial trajectories. It's complete. It's globally optimal within the convex decomposition. But maybe what's surprising is that we can solve it really efficiently. Okay. So the key ingredients behind that are, first, taking the graph search view, but bringing it over into optimization. There's always been an optimization view of graph search. If you just want to solve shortest path on the problem on a graph, you could do that with a linear program. Okay, and that's going to be an important piece of the puzzle. And then we've already had, again, convex formulations of continuous motion planning. If you don't have obstacle constraints, or if you know that you've already chosen to go left or right of the obstacle, that we knew for a long time how to do continuous convex formulations of motion planning. We've seen it in kinematic trajectory optimization. We've seen it in minimum snap trajectories for quad rotors. What's new is putting those together so that it's very efficient, using this graph of convex sets machinery that I hope you'll understand well by the end. And we had to, in order to do it in configuration space, we had to figure out how to make these large regions that are certifiably safe in configuration space. So that's the basic recipe. You guys please feel free to ask questions anytime. That's the basic recipe. I don't think that part's surprising. I think what's surprising is the machinery works really, really, really well. Okay, so let me step through and try to explain, piece by piece how that works. I really want to get into the details with you. Okay, so let's think about just what is motion planning as an optimization. Take my toy example. This is why I kept it particularly simple. So I'm going to parameterize a trajectory optimization problem, a small optimization problem, with just a handful of decision variables. I'll just put a XY coordinate of this, just pick a fixed number of points, right? Write an optimization. I make some squared distances between those points, for instance. I'll do a constrained optimization subject to the constraint of the initial condition being at the start, the final position being at the goal. And then I'm going to add this one ugly constraint, which just says, this is the collision avoidance constraint. In the particular case of a unit L1 ball obstacle, I can just write it in a single line like this. It says all of my x's need to be outside the unit, that red box. Okay, and this is a perfectly good optimization problem. I can hand it to a sequential convex optimization problem solver or something like this and do pretty well. But it's non-convex, so I'll actually do that here. Of course, right? All right, here's my little trajectory optimization. I took out the piece about cutting out the corner just to keep the code exactly like what I wrote on the board. And I can move it around and it solves it interactive. This is a simple problem. Solves at interactive rates on my laptop, of course. I can move the start and the goal around. Okay, but as impressive and awesome as it is, it's a local optimization. And if I start going to the other side of the obstacle, if it's doing a real-time solve like this, nothing that I do is going to get it to stop thinking about going right around the obstacle and start going left around the obstacle. It's stuck in a local minima, and these methods are fundamentally subject to local minima, right? So in order to get to the better solution, the obvious better solution on the other side, the costs or the constraints would have to be violated to move those points through incrementally with a gradient-based method.
So did you initialize it from the previous solution?
Yep, so this is a warm starting solution. So I think it's a guess from the previous solution. Yes, and therefore it gets stuck.
So what's the reason of this solver to fail in such cases?
So I'd say it's any gradient-based method that's trying to incrementally improve the solution is at a local optimum, right? So it would have to get worse in order, it would have to go uphill before it goes back downhill to get on the other side. Great. I appreciate the questions. That's good. Okay, so we can do better with one other thing I want to say that I don't like about that is that I had to pick beforehand the number of samples. I always hated that about trajectory optimization. Sample-based motion planning never had that problem, and I love that, but motion planning has always had that. Or trajectory, most of my trajectory optimization formulations have had that problem. Okay, we've known for a long time how to do planning as a mixed integer optimization. So what does that look like in this case? The beginning, the preamble looks exactly the same, but I'm going to formulate the collision avoidance constraints differently. Okay, so I could say that this is a convex constraint. I'm going to say that xn is outside that face. That's a convex constraint. Okay, or it's outside this face, or it's outside this face, or it's outside this face. Okay, if I put these together, writing a program that has these or constraints, disjunctive constraints, is something that you can write down as an integer program. Okay, you can use binary variables, you can hand it to a mixed integer convex solver, and you can solve this to global optimality, which of course I can do. So here's the now global version of that. So I can move it around. It solves, again, this is a trivial problem, but it solves, as you'd expect, beautifully to global optimality. Okay, so let me just say a word about mixed integer programs, right? So a mixed integer program is a program that's got all of our standard objective and constraints, some decision variables. The only difference, of course, is that I have some decision variables which are restricted to be, if this is a mixed binary program, it's going to be restricted to be either 0 or 1, right? Not between 0 and 1, but 0 or 1. Okay, if I have some decision variables restricted like this, then that's a mixed integer or mixed binary program in this case. It's mixed integer convex if f and g are all convex. And mixed integers convex is extremely powerful because if I take this convex relaxation, then I can use really strong, if I can replace this constraint with the b being between 0 and 1, I have really strong branch and bound type approaches to solve this problem. Now, I want you to make sure you understand what it means for a convex relaxation to be tight. Okay, so this relaxation makes the problem easier. I've taken 0 to 1, say it's between 0 and 1. But I'm going to say the convex relaxation is tight if when I solve the relaxed version of the problem, the solution is also a solution to the original problem. Okay, so if I solve this relaxed version and the answer comes out that b is always either 0 or 1, then that's a tight relaxation. And you can talk about the tightness of the relaxation and how close that works. But in the strict sense, it's either tight, it's tight if you get the right solution. Okay, so the way branch and bound works is it solves this incrementally it starts by solving a relaxed version of the problem completely. It gets some values for the binary variables. Okay, and then it says, I'm gonna split. I'm saying, well, B0 was close to 0.9. So it's probably 1. Let me try making it 1, but I also, just to make sure, I'm going to also try making it 0. Okay, and then I'll solve another convex problem with that extra constraint, and I can go through until I find exactly the right solution. And the key idea is, because I have lower bounds from any convex relaxation and upper bounds from any feasible solution, that I really don't have to, typically I don't have to explore very much of this super exhaustive tree to find the solution, right? So the convex relaxations help you guide the search. The convex relaxations provide lower bounds, feasible solutions provide upper bounds. Okay, but people hear branch and bound, they hear mixed integer, whatever, they say, that's Turing complete and that's going to take forever to run. And that's true sometimes, but there are good mixed integer programs too. Okay, so the performance of this branch and bound depends dramatically, first of all, on the number of binary variables, but also on the tightness of the convex relaxation. And you can see that from the super simple illustration. If these convex relaxations are very tight, that means the lower bound is close to the upper bound, and it allows me to rule out huge parts of the search space very, very quickly. Okay, so the tighter my convex relaxation is, the faster my branch and bound runs. It has to evaluate many, many less optimizations. And I think maybe we don't often talk about how tight the relaxation is, but that's super important. The mixed integer motion planning I just wrote down is not tight. It's got way too many integer variables, first of all, which in my mind is a false combinatorial complexity, right? There is a combinatorial problem motion planning. I had to decide, make one decision. Am I going to go right around the obstacle or left around the obstacle? But the way I've written it is I'm going to make n decisions. Is 0.1 to the right? Is 0.2 to the right? Is 0.3 to the right? I'm independently solving for every one of those points this decision, which of course should be correlated, right? And you can add in things that make them more correlated, but it doesn't strengthen the relaxation action. So it's got too many integer variables, false combinatorial complexity, and these disjunctive programming formulations sort of fundamentally lead to loose relaxations. If I run the same optimization now, but solve the convex relaxation of the mixed integer program, then it's just not good, right? The relaxed version of the problem, which is saying I could be on the top right or the top left or the bottom, the average of that, the relaxation just goes right through the middle. It hasn't captured the essence of the problem in any way, okay? As a result, I have lots of integer variables, I have loose convex relaxations, and I have a sad time solving the problem. It takes a lot of branch and bound to get to the solution.
One clarification in this figure, how did you use the top solution? Because you're still expanding the whole tree, 0, 1, 0, 1. Like, do you cut, like, you give low weightage to the 0, B0 equal to 0 branch?
So for instance, if the top solution is solved and the convex relaxation is tight, then I'm completely done.
Yeah.
Right? If it's a lower bound or upper bound, depending on the lower bound and upper bound, I mean, so you only get a lower bound from the convex solve. I should say that if it's not feasible solution, then you only get a lower bound. But if there's all these cutting strategies of deciding which way to go down the tree. Maybe because I have this one's closer to 1, then I'll choose to branch that. But there's actually very advanced branching strategies that a program like Arobi would use to do that make a strong search through the tree. Okay, so I didn't introduce properly my collaborators, but Tobia, Jack, and Pablo were just awesome collaborators on this. Pablo is not, so someone thought I was talking about Pablo as a student. Pablo is a senior. He's someone that I very much look up to, Pablo Carrillo, the optimization guru. Okay, and he asked the right question. I was always complaining our contact problems have loose relaxations, whatever. And he says, okay, stop saying that. Why exactly are your convex relaxations so loose? He says, for instance, we know that the LP formulation of the shortest path problem has a tight convex relaxation. So why the heck are yours so loose? That's a fair question. Let's figure that out. And it turns out that took us down a journey where we now have tight convex relaxations. Okay, so the shortest, let me just tell you quickly, the shortest path, it's a good thing to know. Shortest path on a graph, if I just go to a completely discrete case, I have a directed graph, a start and a source and a target. vertices V, directed edges E, they'll even have each have a cost. Okay, you can write the shortest path graph search problem as a linear program. So I put binary variables on the edges, okay, and I have costs on the edges too. And if you just sum up the costs of the edges that are 1, if it's in the shortest path, or 0 otherwise, is the formulation, then this is just the path length. Just the sum of the active edges. And then I have an extra constraint, which are the flow constraints. It's just a clever way to say that if I'm in a cell that's on, then the edge in the sum of the edges in has to equal the sum of the edges out. The extra terms are just to handle the special case of the target and the source. But basically the sum of the edges in is the sum of the edges out is a clever way to write 0 or 1. They have to both be 0 or both be 1. And then you would normally say that the binary variables have to be 0 or 1. But a well-known result from linear programming is that if I relax it, I don't even need to say between 0 and 1. I can just say greater than 0. The flow constraints handle the greater than 1. Then that's the convex relaxation of a mixed integer program, but it's always tight. So if you solve this problem, you will get an integer feasible solution, and it's the solution to the shortest path problem. Okay, so that's a good thing to have. And it led to our now generalization of that problem to embrace the continuous part of the problem. Okay, so the new abstraction, which is bigger than motion planning, is this notion of graphs of convex sets. Okay, so I want to still do a graph search problem, but I'm going to associate a continuous convex set with every vertex in the graph. Okay, so every time if you were to visit the vertex on the shortest path, then you're going to pick one element out of a continuous set, and you're allowed to put the edge lengths as functions, convex functions of the distance between, or whatever metric between those points. Okay, the edge length is a convex function of those decision variables. Right, that's a simple transcription, but it turns out to be a powerful one that has strong formulations and fits a lot of interesting problems. I feel bad. These are blue regions. They're not obstacles. In this case, you're trying to be inside the blue region in this abstraction. Okay, so we had the original shortest path formulation from linear programming, and we actually don't have to do very much to turn it into the convex sets version. The edge cost was a constant. Now it's a convex, or it's a function, a convex function of the decision variables x and xi and xj. Each xi has to be inside the convex set. Okay, and the rest of the things basically stay the same. This looks like it should be non-convex, but it's actually a convex function. You can play some tricks with perspective functions to write that as a convex. Any convex set, if you're going to multiply that by a positive variable, in this case between 0 and 1, then that collapses to the origin and grows up. That's the perspective function of a convex set. So this is still a convex formulation. And when we started formulating problems like this, we achieved orders of magnitude speed up over the original motion planning problems. And I'll show you the way that sort of plays out. But again, what matters is the tightness. For performance, what really matters is the tightness of the convex relaxation. So Tobia, the student, was studying this convex relaxation, applying it on lots of even simple graph problems, so discrete plus continuous graph problems. And we knew when it was tight, when it was not tight. And there were a few cases where it was not tight that seemed like, there's kind of a clear lower bound there. And Pablo's intuition was very interesting to me, actually. He basically says, if the solution is not tight in this example, then you've missed a constraint in your linear programming formulation. He had this intuition that basically, I think it maybe boils down to says LP is always smarter than a human. Okay, if a human can come up with a trivial lower bound, then the optimizer should absolutely be doing that. You've missed a constraint. Okay, so we went hunting for these constraints. And the idea, we didn't miss any constraints to get the right optimal solution of the integer variables. But there's an important idea in optimization of adding additional constraints that don't change the optimal solution, but they tighten the relaxation. So there's a reformulation linearization technique is one way, RLT is one way that people do this. There's a lot of different ways that this comes up in optimization, but we're going to add additional constraints which don't change the optimal solution, but when they're but the relaxed solution will be tighter. And the most important one of those was the conservation of spatial flow. So we took the original conservation of flow and we made a spatial version of that where we multiplied we basically said the continuous variables, when the edge gets turned off, those continuous variables also have to shrink to the origin. That doesn't change anything about the optimal solution, but it had a huge difference. It made a huge difference to the convex relaxation.
So in the previous slide, when you had the convex, the coefficient Lij.
Yeah.
Is it just unconstrained? Like
It's got to be a convex
just a
function.
convex function, but
Yeah.
And you pick the parameters of this, or
Yep. So it's,
do you hand define this Lij?
so we have a kind of a rich mathematical programming library. You say add a quadratic cost, or add a linear cost, or add a, all these different sort of costs and constraints you can add. You can add L2 norm cost, all these things.
So the only thing that you are saying is Lij should be convex. It can be any.
Yep. In fact, it can actually be infinite, so it can represent constraints too. So, but as long as it's convex, we're good.
Okay, and you can specify that in the computer program.
Yep. So the human says the shortest path, I'm going to define it as Euclidean shortest path, for instance. Could be a common choice. Or I'll show you all the ones we use for motion type. Okay, so now we're writing down a similar optimization. It's a mixed integer optimization. Okay, but in my mind, we've broken importantly the over combinatorial optimization, and now we're writing it on a graph. Okay, where it's actually deciding, am I going left or right? And it's not adding this artificial combinatorial complexity. Okay, and of course, we can solve it to optimality in interactive rates. Okay. Oops, I did the wrong one. Okay, so now we get beautiful solutions, at interactive rates, same thing we did before. But the cool thing is, this is actually running the convex relaxation. So the convex relaxation is tight. The convex relaxation is capturing the essence of the problem. It will not suddenly get solutions inside the obstacle. Yes.
So the original formulation, which did not involve the continuous space, already had some flow constraints there. So what are the additional flow constraints that you're talking about?
The LP graph formulation has flow constraints, which basically just says that
Hey, Russ, sorry to interrupt. Can you, for us in TV land, can you repeat the question?
Totally, Howie, I should have known that. Yes, I got it. So the question was roughly, what was I talking about with the conservation of flow constraints? And can I just maybe say that again a little bit more clearly? Yeah. So the original LP formulation of graph search has something called the conservation of flow, which says the sum of the edges going into any one vertex has to equal the sum of the edges coming out, which is a clever way of saying either the vertex is in the shortest path or it's not. So either the sum is going to be 0 or the sum is 1. Okay. And what we're going to say now is that the sum of the continuous variables coming in is also going to be either 0 or x, basically. So it's basically just an extra thing saying, by the way, if there's no edges coming in, then x must be 0. That would have been true at the optimal solution, but but when the binaries are 0.5 or something like this, then because of the relaxation, then it has extra strength, and it makes the convex relaxation tighter. These constraints are convex. Oh, sorry, it looks non-convex. It looks like it's bilinear, but it's the same perspective function tricks. But you can still write that as a convex function because those binary variables are 0 to 1 times some convex thing. So it's actually still a perspective function and it's still a convex constraint. Good question. Yeah. Yeah.
Just to make sure I'm understanding this, in this particular example, you've like hand built a graph for this problem with one vertex.
Yep.
Essentially, which is that little point.
Oh, no, sorry, the vertex, the graph is this.
Okay.
Yeah. So it's roughly what you would have done in the original mixed integer formulation, but now we have an entire trajectory in each region. What you're going to see. Okay, so here's our original what if it's a maze? And it turns out actually, if you just grab mazes off the paper, they only have a unique solution almost always. So that wasn't very interesting. So we have a maze, but we started blowing out walls. So there's multiple solutions. And then we got an interesting problem. And you ask to find the shortest path through the complicated maze, but now with curvature constraints and other things. And it's, finds path from the start to the goal, and it's solving it with the convex relaxation. So we're writing a mixed integer problem, but we solve the convex relaxation. That first step of about says I'm done. The binary variables were all 0 or 1. From a graph search perspective, this is an easy problem, but from a motion planning perspective, it's a hard problem. Yeah.
You said there was a trajectory of each region or the case.
Yep. Yep. So that'll be super clear in just a minute. If it's not in a few minutes, please ask me. And to write that down in some of the previous formulations, it would have been intractable. Okay, so there's a lot of work out there about Euclidean shortest path. So this is a generalization of the discrete shortest path. If I were to just pick one point in there, but if I'm now minimizing the Euclidean distance between the points, that's a generalization, but it's a well-studied one. There's polynomial time algorithms in 2D with visibility graph constructions, but it's known to be NP hard in 3 dimensions, and there's actually not much known about dimensions greater than 4. So I'm not breaking any of those fundamental laws. P is not equal to NP in any way, but what we have is a polynomial time algorithm for dimensions for any dimension greater than 4, and all I can say it's often tight. But there must be problem instances where it's not tight. Otherwise, P would equal NP. Okay, so what I'm saying is statistically, almost always, everything we've tried it on is tight. Yeah.
In the compilation of the problem, do you heuristically guess the number of states on your path, or?
No, the question was, in our formulation, do we heuristically set the number of things? That's what we've always had. Sorry, have we heuristically chosen the number of points? The answer is no. What we have to do is we have to do a decomposition of the free space, and then the number of points is basically the length of the shortest path. The same way it would be if you think about the graph version of that. I don't have to preordain the length of the path. It's whatever the path through the graph came up with has a length. So there's of course a maximum number of vertices in the graph, or is it upper bound? But that's a vacuous upper bound. It finds whatever path it needs to find in the graph. What's interesting is you can also add more interesting constraints like dynamic constraints, as we'll see. Yeah.
So in the integer programming case, or the mixed integer case,
Yeah.
you were earlier, like every point along the trajectory was a different binary constraint.
Yes,
And in your case, that's not the case, because you're tying it to the convex function.
that's correct. So
Is that convex L, is that the only way that you're tying all the points together?
good. So the question was, originally in my original formulation, I had X 0, X1 through Xn, every one of them had a binary constraint. The biggest change in the formulation perspective is that I've moved the binaries to the edges instead of on the vertices. That's one big change. And then all of this extra machinery that can push down on the convex relaxation. But making the edges be the binary variables instead of the vertices is a big difference. It changes, for instance, not having to know the length. Yes.
One advantage of the graph search formulation is that you don't have to explicitly construct the entire graph. You can implicitly keep constructing it. But in the LP formulation, you would have to explicitly have variables for every possible transition. Doesn't that lead to
I love that question. So the question is, so the reason it's LP shortest path on a graph is cute, but nobody uses it because you'd have to put the entire graph in memory, and we don't want to do that for very large graphs. And you're absolutely right. And I think we're going to go through the same evolution. Ram's doing the incremental version of this here, and there's an incremental version of this. I won't actually get to it in this talk. We've only started thinking about it, but absolutely the road forward for scaling is doing incremental versions of this. I'll talk to it a bit at the end. Great question. Just a few quick comments, just to make it, you realize that the formulation is good, I think. So when you take those sets X and you shrink them down to points, then you get the original tightness result in the LP formulation. We haven't broken the basic properties, right? But we also know that there are instances of the problem that are NP hard. So there must be lurking inside here some solutions where the convex relaxation is not tight. We have examples of the bad cases, but they don't tend to show up. They're not plaguing us in our motion planning problems. And the cool thing is we can add things like linear dynamics or piecewise affine dynamics and to the edges and start doing, so you can do LQR, finite horizon LQR, or finite horizon piecewise affine quadratic regulator in this formulation. The first thing we applied it to was our favorite old mixed integer footstep planning for for humanoids. And just, there's been many ways I could sort of talk about this, but the simplest thing is that the lower bound from the convex relaxation, if you take at the percentage of the true solution that it captured, all of our best formulations, the best formulations from the literature, the best of them was getting 7% of the optimal solution. Now we're getting 80%. So we got a much tighter convex relaxation. In practice, it's a little harder to quantify, but it's orders of magnitude faster to solve. It just searched many, many fewer nodes in the branch and bound tree, like orders of magnitude fewer. And that's with linear dynamic constraints. Okay, so I realized I should have given this to you earlier because everybody's thinking about it, which is great. So how exactly did we put the curves and stuff like this? Why do I, how am I getting graphs of arbitrary length? So here's how we do the smooth curves. Okay, so now my red is my obstacle. My blue is a convex decomposition. That sounds hard. I'll talk about how we do that, but in the simple examples, it's easy. So I've made 5 convex regions. Okay, I'm going to make a graph where I put an edge, a directed edge, but in both directions, anytime the sets overlap. Okay. And then inside the decision variables associated with the set for each of those, it's not actually one point, but the parameters of an entire curve. Okay, and we use Bezier curves in order to exploit their convex Hull property and keep so that we know that if the control points of the Bezier curve are inside the region, then we have a guarantee that the entire curve is inside the region. If you know that stuff, that's helpful. If not, it was too fast, but we have a guarantee that the entire curve is inside the region. Okay, and then we have constraints on the edges so that if the edge is in the shortest path, then the curve must connect. And it connects with whatever derivative constraints, which are convex constraints. We could say it's smooth up to whatever degree you'd like. And then because we don't want to preordain the timing, we actually have a separate polynomial associated with each region that's allowed a time rescaling. And it's actually not just a scalar rescaling, it's a polynomial rescaling so that we get smoothness all the way through. So each of those sets is actually like the Cartesian product of a lot of control points plus the polynomials. It's a bigger set. It's not just one point in the space. Okay, and then what costs and constraints do we actually put on there? We can handle duration. We can say shortest time. We can say shortest path. We could put some, shortest velocity, kind of path energy. We can put constraints of the form of any continuous derivatives. We have collision avoidance constraints that happen for all t, not at sample points, right? It's stronger than saying I sampled long enough and might cut a corner or something. This is actually a guarantee that for all t, it's collision free. I can put velocity constraints. I really want the next build to be acceleration constraints, but I can't do it. I can't do that yet. So we can do it if we have fixed the timing, but we can't do the timing and the acceleration constraints jointly in a convex formulation. And then you can do, put bounds on all the things. So that turns out to be really useful for planning. So that's a big class of problems that we can do. And if you put it on these simple problems, you can change your objective by different paths through the graph, right? This is solving more than the graph search, right? Is that clear? Yeah. Okay, just to make sure I didn't sort of oversell anything here. What we have is a transcription to a mixed integer convex program. So you can always, but the relaxation is very tight. So with the guarantee I can say is that you can solve the global optimality with branch and bound. In practice, it's orders of magnitude faster than previous work. So you can always get the global optimal solution with this method within the class of curves, right? I've picked some degree of polynomials. I've trained them with Bezier, constraints and stuff like that. But if you're willing to solve the mixed integer problem, I can guarantee you'll get global optimality in that class of curves. But what's cool is that solving only the convex optimization, just that first step, you don't even need a mixed integer solver, plus a little bit of rounding where if you get something that was 0.99, you find that there's some importantly, maybe a little sophisticated ways to round, okay? It turns out that is almost always sufficient to obtain the global optimal solution on the problems we've looked at. Okay, so to tell you that, I just have to tell you statistically, right? That's just like how often is it optimal, right? So we did things like take our quadrotor environment, we procedurally generate a bunch of buildings for it to fly through with lots of complicated corridors and stuff like this. And we just asked how often is the solution to the convex optimization exactly the solution to the mixed integer optimization? And it's, almost always. And even when it wasn't, its solution was very close to optimal. There's a kind of an interesting thing, which is you can get the convex relaxation to give you the optimal solution, but it also gives you a lower bound. And so there's a second question is, does the lower bound certify that you're optimal? How often does it actually the case that the lower bound and the upper bound match after some rounding? Okay. So without even solving the mixed energy, you can be confident that you're optimal. And that's a lower percentage, but still very close to optimal without even needing the branch and bound solve. Okay. And then the last piece of this is, how do we get the convex regions? We've for a while played with something called Iris that some of you know, which is our fast approximate convex segmentation. Robin Dietz did this back in 2014. He was trying to do it for humanoids walking on rough terrain and using real sensor data. And he was saying, I'm just trying to find big convex regions. And he's got a alternation between a large scale quadratic program and a relatively small semi-definite program to do that, the ellipsoidal maximum inscribed ellipse. And that worked in high dimensions, millions of obstacles, and worked even on raw sensor data. And so his work back then was saying, I'm going to do motion planning by decomposing my space, right, into big convex regions that had to live in the Euclidean space. Okay, and then he was solving the harder version of the mixed energy that didn't have the strong performance. We had to wait for longer solve times. He was able to solve the global optimality. What we've done now is taken Robin's insights and tried to extend them into configuration space, which is way ugly, right? The original Iris assumed that all the obstacles were convex. And so now, configuration space obstacles are not convex. You take a nice convex obstacle in 3D, you move it through into joint space, and it's an ugly curve, right? This is just two almost welded EWAs moving around, but then the obstacle looks like this weird red thing. Okay, so but you can still do it. We have two versions of it. We have a SNOPed nonlinear optimization version that's super fast, but we also have a sums of squares with rigorous certification that works nicely by and scales to the big problems. So we just assume that each region, we do a convex decomposition of the geometry in the original space, in Cartesian space, okay? And then we search for certificates in joint space and big convex regions in joint space. And we do that by certificates. We use rational polynomial dynamics of the manipulator. We find certificates that are separating hyperplanes, guaranteeing that these obstacles are always, for all Q inside the region, are always collision free, and up to SDP accuracy, numerical accuracy. These are certificates. I'll skip through that a little bit fast here. But what's cool about it is that these have been successful beyond my wildest dreams, I guess. So it finds, you might think that these are going to only find things that there's going to be some gap between the sums of squares and the true curves or whatever, but we're finding right up to these really complicated boundaries, sub-millimeter or millimeter precision on big EWAs in 14 dimensions. We're getting really nice convex regions. And, this is an example where we seeded it with the geometry of the mug and the shelf. Okay. Okay, so it's got all the geometry of the fingers, of the mug, of the shelf. It's trying to avoid collisions and using sums of squares or SNOP to find the regions. And then it's hard to visualize 7-dimensional regions. So I'm just doing a random walk inside this big configuration space polytope to sort of show. And it started here, but it's finding this big volume of really useful, good space around the objects. Okay, and it turns out that even for very complicated manipulation tasks that we've seen, 7 to 20 kind of regions fill a huge part of the space, even though there's an ugly configuration space. So we did some comparisons with PRMs and the like, and the rough story, at least for our admittedly not super optimized PRM, but we build our graphs, we do our pre-computation of these iris regions ahead of time in less time than we could build a 10,000 or comparable PRM, and we solve, better trajectories. They're more optimal, faster than with the PRM. And in a few cases, it's way faster because we do some pre-processing on the graph, and we can sometimes realize, even with our preprocessor, what the path has to be through the graph, and then it really just becomes a trivial convex optimization. It solves lightning fast. So we have extensions of this in all kinds of directions. So we've been working on doing graphs of geodesically convex sets, okay, to operate on manifolds. And one example of that is just making sure that we can handle, that's unfortunate, but we can handle mobile bases and don't worry about wraparounds in pi and things like that, but we're also working on trying to do it on contact manifolds. There's versions of GCS that extend beyond motion planning, right? So it's a more general framework. It's already orders of magnitude faster for a bunch of mixed combinatorial continuous problems that have a graph network flow kind of interpretation. You can take your favorite network flow algorithm, you can add convex sets, and then you can try to use the graph of convex sets machinery to tighten the relaxation around that. So for a traveling salesman problem with neighborhoods is kind of a similar problem where we have better solutions and things like that. LQR fits into this for control. Piecewise affine systems fit into this for control. It works for task and motion planning. This is the beginning of a story about this. This is just thinking about a very simple version of task and motion planning where you can pick and place boxes. The interesting thing was that, so the one I'll show is from a top down. So that's the same sort of arm coming down and moving the boxes, and it has to rearrange the boxes. The interesting thing is if you just make the graph here and ask for the shortest path from the initial state to the final state, the graph has all kinds of symmetry because it doesn't really matter which box you order first. And we realized that it's not well formulated as a shortest path problem. It's actually better formulated as a traveling salesman problem. So the TSP formulations of the graph with the graph of convex set machinery gave us tight relaxations. We could solve, bigger problems with lots of boxes moving around and the like. It's actually, there's fun puzzles. Sudoku, I'm sorry, Sokoban, I guess it's Sudoku, but Sokoban kind of puzzles that we can solve at a small scale. So we'll see how far we go. Again, I think at some point we have to not put the entire graph in memory. Yeah. Okay, as a motion planning tool, right? This is, I'd say, version 0.1 of a framework, right? So it's competitive, better than, it plans better paths faster on higher degrees of freedom. So one of the motivations, one of the reasons I like the bimanual mobile manipulator case is we're talking about 17 degrees of freedom that we're making these plans in. And, that's hard to do. Most people who are doing sample-based planning in 17 with a bimanual setup typically will freeze one arm, plan the second, maybe then use this as a dynamic obstacle for the first one. You have to play these games to do sample-based planning in high dimensions. And this is able to go up into those higher dimensions. But there's a lot more to do. We're scaling, we're working with Stephen Boyd on a custom solver now. Tobia's got a version that solves really big problem instances. We're going to try to bring that online. It has some restrictions, but it's a very promising direction. He's doing minimum snack trajectories of 10K regions with clever preprocessing and not putting the whole thing in one optimization. And there's a version of this in our, that we pushed to the open source project Drake. So the graph of convex sets, the abstract class is all in C++ and mature and hardened. The motion planning transcription is in a Python notebook associated with the paper and will be in here soon. Okay, so yeah, that's our new strong mixed integer convex formulation of shortest path over convex sets, right? We reduced the shortest path problem as regions. When we reduce the regions to points, then everything's traditionally good is still good. The problem is NP hard, but we have strong formulations and very efficient branch and bound. And the cool thing is that the convex relaxations are often tight. So with a little bit of rounding, we never have to call a mixed integer solver. And then the initial application that I kind of used to buttress the talk, but is the motion planning, manipulator planning at the dynamic limits. And I hope you see that this is like a step on the road, my journey of trying to understand combinatorial optimization and how it should connect to trajectory optimization. And the large scale search is the next step. Yep, I always try to plug the classes just in case. Yeah. Cool. I'll take any questions. Yeah.
So you say that this framework is a good replacement for this hierarchical local planning that people commonly use in quantitative literature or like literature. Would you say that now you can have a single layer that does the global plan and is also dynamic?
Great. So the question was, how well does this encapsulate the sort of the hierarchical global plan, local plan? So the version I talked about today, the one we have the strongest results for, is restricted in the sense that we understood the convex formulation case. So that I think most people would be surprised how many things you can fit into the convex formulation. All these curvature constraints and higher order polynomials and all these other things. Perspective functions are, you might not think it's convex, but it is convex. But you might have things in your hierarchical quadruped that don't fit yet. I think there's natural extensions to doing some nonlinear optimization using the same machinery to get the efficiency of the graph search, but that's work to be done. That was part of my future work. The goal is, yes, to try to combine the discrete decisions you're making with the continuous decisions in a strong way. And maybe to Ram, right? One of the important things that is that the continuous variables and the discrete variables really interact. So it's not the case that if I were to just add one more set, I have to resolve the entire thing because the curvature constraints early on affect even the feasibility of whether I can be in this set, or certainly the curves in this, the variables in this set. So it's really solving jointly those two problems, which can be good because the continuous variables put pressure on the graph, and the graph puts pressure on the continuous variables so that they can kind of help each other, right? It's a harder problem, but some of the reasons why you would go left or right around the tree are because the wind's blowing and my quadrotor only has certain, prop limits or something like that. So that, that reasoning pushed up to the graph search can help your combinatorial search.
Then I had a follow-up.
Yeah.
You showed the two robot manipulation example.
Yeah.
So in that case, are you doing one trajectory at a time, or how does that vary? You plan one robot, or are you planning in the same joint space? How does that?
17 degrees of freedom, or that one was 14, I guess. The bimanual was 2 7-degree of freedom arms. We're optimizing them jointly in the 14-dimensional configuration space. Yeah, it's one big, and the iris regions are in the configuration, the 14-dimensional space. Yeah, they make big convex optimizations, but they solve efficiently. Yes.
So when you're solving the sum of square programming, so does your solver always give a feasible solution for every time, or the failure cases increases as your dimension increase?
Good question. So in the iris computation, where we're certifying regions, we use sums of squares. Sums of squares has different properties depending on the different formulations. This is a stronger case than a lot of cases because the polynomials are degree bounded. Even the volumes are bounded. So it's actually Archimedean. It's a straightly stronger class of polynomials we're looking over, and we have some stronger guarantees about upper bounds on degree, so the monomials and stuff like this. It's not to say we're free of numerical issues, but we've seen success all the way up here. I could ask, the guys, did you ever see numerical infeasibility? They might say yes. I wouldn't be surprised if they said yes, but these are pretty good cases of SOS problems.
So you also mentioned that statistically in high dimensional system, your solution can always give a global optimality. So is it because your solution is robust to all types of problems, or you can build a type of problem where the failure cases would increase of your solution?
Okay, so we know there's some instances that are NP hard, which means there are cases where the branch and bound could take exponential time to find a solution. So I haven't gotten around that, but we're saying in most instances it very quickly finds a solution.
But do you have built any cases?
Yeah, we have there's actually very simple cases where the convex, it's fine to be exponential in 3 variables or something, right? So we have very simple cases where the branch and bound is inefficient, but they are contrived cases. They haven't shown up in our real problems.
Thank you.
Mm-hmm. Yes.
Does this approach extend to robust planning?
Good question. So does this, there are many ways to think about robust planning. You could do, Gaussians, you could try to do worst case planning. I think many of them, the machinery is very general, right? So the problem becomes, how do you transcribe that problem into a graph of convex sets, right? So a lot of people, like for linear polytopic regions propagating through, that should fit in immediately, right? The linear quadratic cases, we could probably think about, but there's some of them will snap exactly in. And it's not going to, I mean, I think all the things you can do with convex optimization for robust control will snap in immediately. Yeah.
You call the connection with hybrid system. It's a lot like within each convex set, you have a system load, and the contraction of graph is like the contract the transition matrix for hybrid system.
That's exactly right. So,
Yeah.
So he asked for the comment, the connection with hybrid systems. So in fact, that was the original goal for this, and we're still working on the control through contact version of this. Both the planning through contact and feedback control through contact with it, which is very much a hybrid systems problem. So the limited case of piecewise affine hybrid systems, autonomous hybrid systems with linear guards, and the like, snaps directly in, and we can solve that. I think it's the best that I know of for solving piecewise affine quadratic regulators, for instance. The more general class of hybrid systems involves nonlinear guards and nonlinear dynamics and all these other things. So there's a version of this you could try, but we've studied the case where we can analyze, which is the convex case. Yes.
What's your intuition on how this method would perform as you transition through various discrete modes on your system, the continuous dynamics change in response to that? For example, with the shape change or contact with the surface that affects your system.
Good. So, I mean, it could be connected to the question about robustness. So if I anticipated shape change or something like this, there could be a robust formulation version of that where I'd like to say that this works for all possible shape changes in some range. I could solve that, or maybe might say it's infeasible. But again, this version of it's going to be limited to the convex formulation, which is richer than most people think, but it's going to be limited. Yeah, so you could also take an MPC kind of approach to this. These things should warm start very well. So if you were to, on the fly, you planned optimistically, saying that my guard is going to be somewhere, and then on the fly you realize the shape changed on me. How would you recover? Then that would be quickly adjusting the graph and then planning repeatedly on the fly. And yeah, so I think the warm start solve for this should be very good. So I'm optimistic, but we haven't done that yet. Yeah.
Maybe we can also take questions.
Oh, sure.
Offline. We are already over time, so but Russ can be here for 15 more minutes. While
Whatever you like, yeah.
Okay. So let's all thank Russ and